I am just delighted to be here today to see all of these bright-eyed faces. You know, I taught my undergraduates this morning, and now I'm looking forward to really an engaged crowd. So I'm going to talk about the universe at the ripe young age of 1 second, and in particular, I'll get to an experimental project, the only type of its kind in the world, which in fact would not have been possible without support from the Simons Foundation, where we're trying to look back at this very early time. So let me start with these two celestial globes. You might, sort of, if you've gone to some of the older museums, like above the Place de San Marco in Venice, you might be familiar with these old celestial globes on the left. In fact, they have the 48 constellations categorized by Ptolemy, who was a 2nd century astronomer. And they show you what it would look like to look up in the sky, to look at the constellations. And it reminds me of Olber's paradox. For those of you who know this paradox, it's the question of why is the sky dark at night? Why isn't it bright? And the idea is simple, which is that if the universe has infinite extent and stochastically uniform distribution of luminal objects through it, and you can see light from back as far as you can imagine, then since the light falls off as 1 over r squared from the luminal object, you get a compensation for that by the fact that you see r squared more luminal objects as you go farther and farther away. So in principle, as you look at any direction, you'll eventually be looking at a star, and so the sky should be bright. But it's not bright. So is there something about our assumptions about how long the universe, how far back we can see light, and also whether that light has remained the same through the evolution of the universe? On the right is a much more recent celestial globe, one that's this was from the Wilkinson microwave anisotropy probe in 2009, and more precision versions of this are being measured. It also has a deep paradox in it. It first of all tells us that in fact at some point in the early universe, everything was bright. It was bright everywhere in every direction. And not only that, if I were to look in the sky at different points of the sky, it was sort of the same level of brightness, or if in fact the distribution is related to the temperature of the plasma that produced the light, and the plasma is uniform to the level of a few parts per million in uniformity. And that gives us another paradox, because if you imagine sitting on the Earth and looking at this direction and at this direction, and you find that the temperature is good to 10 parts in a million, your frying pan, you can't keep it accurate to 10 parts in a million. This is only a very small distance. So if you try to resolve the fact that the light that you're seeing is now not bright in optical, but is at lower frequency, you create a model for the universe that we will discuss, which is that the universe is expanding. And then the reason it's not bright anymore is the fact that at some point the universe had expanded to the size that we've gotten to, and the light that was produced at that time got stretched out. So the wavelength of light times its frequency is always a constant. So if you stretch it out, the frequency goes down. And so that when we say the deep space is 2.7 Kelvin, that 2.7 Kelvin was actually 2700 Kelvin, like similar to the temperature of the sun at that time. So if we use the model we understand for extrapolating back to the early universe, we find that if you go back another 400,000 years, we would approach something that looks like a singularity. It would be so dense that that's what we would consider the Big Bang, that all of the universe started at that time, roughly 13.7 billion years ago. At about 400,000 years later, it became optically transparent. That light was emitted, and now we see that light today, but redshifted to the microwave frequency. But the paradox that we run into from this globe is that if we extrapolate back that period of time between when everything presumably started to this point in which the light was emitted, you can form a light cone, which is shown here. And so everything that occurred at this point could have affected the temperature at this point at which the light is emitted. But these two cones never talk to each other. So you get to the sort of obvious scenario where maybe, even though I'm looking this way and this way, maybe at some point way, way far in the past, those two directions connected with each other causally. And so that's sort of, we have to, with every paradox, you have to change your understanding of how you can have a universe that actually has a common past, even from very different points on the sky. But you don't have to go to these to the very early universe to find a paradox. You can find them in our present day universe. So if you imagine backing out of our Milky Way galaxy and looking back in the same way, this is an artist view, we've never achieved that, but in the same way in the 60s when we went in space and we looked back at the Earth, this would be an image of where we live. And we live at roughly 25,000 light years from the center of our Milky Way galaxy, this point here. In fact, I'm told we've recently fallen off of the spiral arm. I don't think that's serious, but we're on a spiral arm. And you'll notice that the center of the galaxy is not exactly point-like. It looks like a bar. And in fact, in 1973, there was an important work by Jerry Oestreicher and Jim Peebles where they studied the stability of spiral galaxies and found that they are unstable. That in fact, one can't really explain why it is that our home in the universe hasn't just been sucked up into a large bar mode, but indeed it is stable. And so they already speculated at that time that we were living in a large halo of mass that stabilizes this spiral galaxy. And we refer to that halo as a dark matter halo. Okay. And so we needed to resolve that paradox. Otherwise, we have this weird condition that we're living in a universe that intrinsically we think from calculation should not be stable. So that's another element. Now, if we look between what happened between these two celestial globes, here where the universe was incredibly uniform, level of 10 to the minus 5, to our late 1500s celestial globe where we see all the constellations. So obviously a lot happened between those two times. And the universe, as subject to the expansion of gravity, started to clump up. At large scales, it's still uniform, at 100 megaparsecs and bigger, but at smaller scales, it is subject to gravitational instability, and we start getting luminal structures forming, and we can, for some of the structures in which there's a known light output, we can actually measure, like such as the supernova 1A type, we can sort of measure how far they are away from us by the fact that we know what their optical output is, and in the fact that it's shifting, we can see how far they are away from, how fast they're recessing. And so this was, for early measurements of galactic and cluster recession, came up with the understanding that we live in a universe which we say is governed by the Hubble law, that objects recess from us in every direction. So every on the objects is recessing from every other object, and the rate of recession is proportional to the distance they are from you. So in fact, if you get very far enough away, things are recessing so fast that they fall out of causal contact. They fall out of your horizon. So that fact that things can be expanding so fast is a key element to the early universe. And we've done amazing things. So we've been able to see that excesses in these small little 10 to the minus 5 excesses that occurred there under our understanding of how gravity evolves actually can be seen in the material footprint of the galaxies that have been formed in the present-day universe. These are called baryon acoustic oscillations. And in fact, the Simons Observatory is increasing the precision in which we understand this microwave radiation that comes from the early universe by orders of magnitude. It's a future project. So what we hope to learn is something more about what's happening at the earlier universe. We have an indication that there was a period in which the light elements were formed. We call that Big Bang nucleosynthesis, and there's a prediction for the relative abundance for helium to hydrogen, which I'll talk about in a little bit. And what I'll be talking about in this talk is the production of a particle called the neutrino that persists to the current day. But let me first go through and collect all of, I would call, the cosmic elements of our understanding of the universe. And one of them is involved with what we call the expansion of the universe. And I was thinking the other day that, living in an expanding universe kind of reminds me of the homework problem my daughter had, which was to construct the hypercube. And the problem is simple. You start with a point, and you expand it to a line, and you expand the line to a square, you expand the square to a cube, and then you expand the cube to the hypercube in some other dimension like time. And so if you think of some box in space and that expands in time, you can imagine it's kind of like a hypercube. It's moving. And in fact, the rate at which things are expanding, you can relate that to a velocity, so the rate of change of that expansion scale. And the velocity scaled as a kinetic energy. And in physics, the laws of motion are governed by balancing kinetic energy and potential energy. And so the potential energy in our universe has to do with how much matter is in this box, and so the energy density. And energy density behaves differently depending what's in the box. So if you have just a collection of particles in the box, which we just call matter, then the energy density goes down when you make the box bigger, if the same number of particles are in there, just like 1 over the volume. So it goes 1 over the third power of the length of one of the legs of the cube. However, if what's in the box is a wavelength of light, when you expand the box, that wavelength gets longer, and the energy goes down because the frequency goes down as the wavelength goes up. And so radiation behaves a little differently. It drops off faster, 1 over the 4th power of the expansion rate. And there's yet another form, which we'll talk about later, which doesn't change when you expand the box, and that's what we call dark energy. So there's one of the, I think, also one of the biggest paradoxes about understanding the current universe is that if you were to look at the ratio of kinetic energy to potential energy, so the rate of change of this box versus what's holding, what's preventing it from escaping this well, inherently it should be very unstable. It should be that this expansion rate changes in such a way that the kinetic and potential energies are unbalanced. That's sort of inherent with the instability of gravity. And so in fact, after a few seconds, not just 1 second, but after a few seconds after the Big Bang, we expect that the ratio of these two quantities to deviate from 1, already at the several percent level, much less at 10 to the 17 seconds where we are today. And what we find is when we measure these two quantities using the cosmic microwave background, that they're accurate to being equal to each other to 0.3%. And so it's a strange thing. And so people tried to figure out how to put something into the universe that would make kinetic and potential energy maintain equality to the present day. And so the idea they came up with is called inflation. The idea being that at the very early stages of the universe, it wasn't expanding very rapidly at all. And that you can imagine sitting on some balloon, surface of some object, and that in this very early stage, it expanded extremely rapidly. And as the balloon expands out, things get flatter and flatter. And it turns out the flatness is also a representation of these two quantities being equal to each other. And then after that point, something happened. Matter and radiation got created, and then the universe started to expand under the potential of the matter and radiation that was created. There is a model for the early universe that would allow it to expand in this way. It basically has nothing else in it except for what is called the cosmological constant or dark energy. And this project, this experiment that I'm proposing is also trying to use these neutrinos to see whether this sort of fantastic idea, if you think about it, it's almost a reverse engineering idea to try to get the right answer by postulating some initial conditions that are extremely precise. In fact, you need something like 60 orders of magnitude of precision in order to get the result that we see. So let me go, before I put all the elements together, to remind you of one other element, which is largely invisible to us, but with a lot of hard work, experimentalists have been able to detect it. In fact, I can quote Wolfgang Pauli, who said, "I've done a terrible thing. Something that a theoretical physicist should never do. I've postulated something that could never be measured experimentally." And he was lamenting over having come up with the concept of the neutrino. And but lo and behold, we have been able to measure neutrinos and learned a great deal from them. Neutrinos are produced at the center of the sun, and we can actually, with large water Cherenkov detectors, measure, a map of the sun from the neutrinos that come from the center of that object. Now, to give you an idea of how hard it is to detect a neutrino, if you wanted to detect one neutrino, that single neutrino, you have to have at least 3 light years of iron before it will actually interact with the iron. But fortunately, in a lot of these processes, they're producing many, many orders of magnitudes of neutrinos, and you can get away with just detecting a few of them. So when I was a graduate student, neutrinos were a problem. They were a problem because there was a prediction for how many neutrinos were supposed to come from the sun, and it didn't match up. So you can imagine, in fact, one of the leaders of that theoretical calculator was John Bacall at the Institute for Advanced Study at Princeton. And you can imagine that physicists were quick to blame the person computing the numbers. Oh, it's the center of the sun, you don't really know what's going on, you got the number wrong. In the end, it had nothing to do with the calculation. Once we understood what was going on, the calculations were accurate. What wasn't accurate was our understanding of this nearly invisible particle. Since it's nearly invisible and it's very light, it can do things that other particles don't do. It can actually transform itself into, among its different states, of which there are 3 of them, coherently as it evolves through space. So what the problem with the experiment is that they were trying to detect the neutrino by looking at some particle associated with it. And the neutrino is like a partner to the electron, lightest neutrino. And so the way we detect the neutrino is we try to get it to produce an electron. But it's also a partner with a heavier version of the electron called the muon, and an even heavier version called the tau. Why there are 3 generations of matter, we don't know. That's one of the other mysteries of why we study particle physics. But it turns out that when you produce neutrinos, they will oscillate between their different flavors. And all you can measure is the relative phases for which, when they're in different flavors. There was a quite ingenious experiment that was built in Sudbury, Canada, called SNOW experiment, that actually managed to design something that measured the flux of neutrinos from the sun independent of what flavor they had, and they were able to verify the solar calculation. But what have we learned? We've learned that the neutrinos have mass, and I can tell you also, it wasn't that long ago in which people were sort of guaranteed the neutrino didn't have mass because it didn't fit into, the mathematics of what was the easiest way to describe matter in a larger multiplet. But now we know they have mass. We know that what's important on this little table is we know that one has at least a mass of 0.05 eV, which is, like a factor of 100 smaller than the energy of one optical photon. So it's a small thing, but it's not so small. And a lot of what I'll talk about today has to do with the fact that this number is big enough that we could actually use it to separate it from other processes if we can get measurements that are at the level of that precision. So we don't know exactly what the masses are because we only measure the phase differences. Also, we don't know exactly which ones are heavy and which ones are light. So there's some ambiguity among the three about the ordering they have in mass. But we know enough about them to know roughly what to look for. So the thermal history of the universe, I can, at least my understanding, I can date it back to this paper from 1965. And in fact, Jim Peebles, who helped write the paper, I saw in the coffee shop the other day, and I asked him where he got the numbers for the density of matter. I didn't know whether they depended on whether it was baryonic or cold matter or just some measure of the overall potentials that they saw in the galaxy large-scale structure, and it's the overall potentials. But it was amazing. He talked about this paper as if he posted it on the archive the night before, much less something as over half a century old. But this is a plot of those numbers I was describing to you. The fact that radiation falls off like 1 over a to the 4th, but matter falls off slower at 1 over a to the 3rd. And so he predicted that there was a point in which matter would be dominant, and when matter is dominant, you can have sound waves. And that's that important feature of those hot and cold spots on that cosmic microwave background. But the other thing that they predicted was that at 1 second after the Big Bang, the universe should become transparent to neutrinos. So the neutrinos that are produced should be able to stream through the universe and go unperturbed while all of these other things are going on. So the neutrinos are actually fairly handy in that way. We can actually not only verify that the right number of neutrinos are coming from the center of the sun, we can see each process that occurs. And in fact, we see it only 8 minutes after it happens. That's the speed of light to the center of the sun. And whereas the optical signal takes about 30,000 years to get to the surface. So if the sun stops burning, we have a 30,000 year head start to get away, which is a useful thing about neutrinos. But it also is a useful thing about trying to figure out what happened at the early universe, because we can see, things that happen that where a lot of the information is retained. So we know a whole lot about these neutrinos. So because we've measured the number of photons from the cosmic microwave background, we can relate that number to the number of neutrinos. So we know there's about 112 of these per species per cubic centimeter everywhere in space on average. We know that they have a distribution of kinetic energies, which is just a little colder than the photons. That's because after they decoupled, the E plus E minus recombined and heated up the photons a little. We also know that they had to have been emitted around this time, because if the neutrinos are in thermal equilibrium, they scramble protons and neutrons. So you can't form any sort of nuclear matter if the neutrinos are still scrambling protons and neutrons. In fact, I have to say the Big Bang nucleosynthesis also solves what I consider a fundamental paradox, which is that a free neutron only lives 15 minutes. It'll decay after that. It's an unstable particle. But without neutrons, there would be nothing interesting, at least in our planet. They're needed to make all the heavy elements. So what made it possible for the neutrons to exist to the current day? What made it possible is the universe was cooling off so rapidly. This rapid fall off was quick enough that it got below a temperature within 1.5 minutes, so that a proton and neutron, which is no longer being scrambled because the neutrinos had just gotten away, they could bind to form deuterium and not be dissociated with all the radiation that's around them. And that process is what kept the neutrons to this day. So all the neutrons we have with us today, barring ones that we produce in colliders, came from the fact that they were held in nuclei 1.5 minutes or within the first few minutes of the universe. And if the neutrinos had not decoupled, that wouldn't have been possible. There's also a special feature of the neutrinos, which is that they were produced relativistically, and they've been cooled down as the universe expanded. In the same way that the light has gone from optical to microwave, the neutrinos went from being relativistic to being, nearly at rest. And what happened is that the distribution of velocities that they would have, if you would be able to detect them, a bound and unbound fraction in galaxies, they have a footprint that came from the fact that they were just cooled down as opposed to just being produced non-relativistically. So we hope to see that. So let me bring all these elements together. And I don't want to poke fun at the cosmologists, but I can't help but thinking that it looks very similar. So you start with 3 elements, they're sort of familiar, photons, and neutrinos, and baryons, which you can almost imagine is like fire, water, and earth. You add a 4th element, which it needs to be there, the dark matter. And then you find out that you need yet a 5th element, the dark energy, to explain the accelerated expansion. So with these 5, primordial elements, you can describe a lot about why our universe came to be what we see. And I plot that here. This is a ratio of the expansion factor. So this was, in the universe, everything was 1 billion times closer to each other than it is today. This is this normalized to the ratio of potential to kinetic energy. This is this unusual fact that it's been near unity throughout the matter radiation-dominated universe. And what happened is our prediction says that there was a mixture of photons and neutrinos in the various early days. As the universe expanded, they dropped in density quicker than the matter, and the matter started to grow. Now, I gave this talk once, and people asked me, why is it the ratio of neutrinos to photons and baryons to cold matter looks similar to each other? I have no idea. There's no real logical way I could explain why that is, but this is the transition between radiation and matter. And then during this period, we were able to get all of this wonderful gravitational clustering that led to our galaxies and supernovae and all these phenomena. And then near the end of the evolution, which we can see from the rate of recession of these type 1a supernova, it seems that the universe is now that the 1/a to the 3rd term has gotten very small, this constant term is filling in. And we call this vacuum energy or dark energy. And so now the universe is expanding away exponentially. So there, to a large extent, the days of large-scale structure formation are now over. Things that were close to each other are going to, gravitate to each other, but now everything is flying away. We're very lucky that this didn't kick in back here, because otherwise there would have been nothing interesting in the universe. So we had this little period of opportunity that we fortunately took advantage of. Now, what happens to the neutrinos is not quite clear. Depending on what the absolute neutrino masses are, they have sort of a different level of role in the formation of galaxies. So because they run really fast, they kind of smooth things out. And people are looking for the point in which they slow down so that they start themselves to be part of the gravitational clustering. And the data is becoming precise enough that we're hopefully will be able to see that. But the project I want to describe to you is I want to try to detect the neutrinos today in the lab and what masses there are, so that we can use this information not only to help the other data that we grab from the cosmic microwave background and from the galaxies to figure out, more about all of these weird paradoxes and whether we've resolved them correctly. But I'll also show you that the neutrinos can maybe tell us something about the earliest times and give us maybe the closest snapshot to what we call inflation. So this is a joke that almost no one likes, but I tell it anyhow. So in 1987, there was a supernova, 1987A, and that was detected by large underground water Trenkov detectors. then the solar neutrino spectrum, which I plot here, which is a bit higher and peaks at about 300 keV, that flux was resolved by using a heavy water detector in Canada. So here is the cosmological neutrino flux, which is even larger but lower energy. So you need even heavier water to do that. But in fact, it's not as crazy an idea as it sounds. So it turns out the heaviest isotope of hydrogen, or a component of water, is tritium. And the reason you would go to tritium is because there's so little energy left in the neutrinos that if you're going to detect them, you can't have any threshold for them to interact with what you're using to detect them. So you need something that is stable, semi-stable, but inherently does decay so that there's no energy threshold. And it just turns out that tritium is really ideal for this. So it has a relatively low energy spectrum for its kinetic energies of its decays, and it lives a relatively long period of time, 12 years. But it's decaying, so you're going to look for something that is sitting on top of a spectrum of tritium decays. And the way you can do this is in a normal case where if you imagine there is a neutron here that's decaying to a proton, emitting these two particles, the electron and electron antineutrino. This process, if you flip this particle to the start, can be a process which detects the neutrino from the Big Bang by absorbing it on this nuclei and producing this electron, which will have more energy than any electron produced in this process, because I've given it that little bit of 0.05 eV of extra energy, and it doesn't have to produce it at the end. So amazingly enough, back in 1962, Steven Weinberg, where, as you can imagine, that was before the 1965 paper. So there wasn't really an idea of how many neutrinos were in the universe. It could have been flooded with neutrinos. And in fact, because neutrinos are spin 1/2 particles, they have the same property that electrons have when you stack them in atoms, which is that they stack onto each other. You can't put identical particles on top of each other. They all have to have their own state. So if you have a universe swarming with neutrinos, there's something called a Fermi energy. You keep stacking the momentum states on top of each other. And so if you were to have a process that produced a neutrino in the final state, if the energy in the neutrino was small enough, it might not be able to be produced, because there might be a neutrino already in that state. And that's a phenomenon we call Pauli blocking, from the same Wolfgang Pauli that I mentioned earlier. And so his idea was that maybe we would see Pauli blocking at the end of the spectrum, and then, in fact, we would see a large rate of captures of those neutrinos because there's so many of them around, they can call the process. Now, then a couple years later, it was turned out that there weren't as many neutrinos as expected. But within the last 2 decades, we've discovered the neutrino has a mass, so this same kind of idea still works. You would be able to see the neutrinos by the fact that the electrons coming from their capture would be displaced from the endpoint. Now, why try to measure these now? This idea was proposed back in the 1960s. No one has done it since then. Well, it turns out now we have a very well-defined range where we expect the neutrino to be. We know that it has to be heavier than 0.05 electron volt from the fact that we see the neutrinos from the sun, and we've resolved how many come from there. We also know that the neutrinos are probably going to be lighter than 0.2 eV, because if they were heavier than that, then they would have become non-relativistic when the light was produced that we see in the cosmic microwave background, and that it was produced about 0.1 eV. So we know that they're sort of lighter than this, heavier than this, and if the technologies exist to be able to measure at this precision, then we have a chance of actually seeing the signal. So experimentally, what we need to do is to figure out whether we can measure this as precisely as we can to see the signal, and then we have to filter all of this out. Now, on sort of a natural consequence of having to do these two things, it's like looking at the sky with a very, very high resolution telescope. It's very hard to see the entire sky with the same level of high resolution. So you have to figure out some dynamical way of knowing when you have to make this very high precision measurement. In the same way that people are now trying to use gravitational waves to go look in the optical to see whether something else like a neutron star merger or something like that. So you have to have more than one signal to be able to cover the phase space. So this led us to developments with graphene, which seems like a big transition from talking about the early universe. Why talk about a two-dimensional material made out of carbon, which in fact we all abundantly used to produce when we wrote our papers in school. In fact, one of the easiest way to get graphene is to scribble on a piece of paper, take some Scotch tape, and then you have to use a microcleaver and you can take off a flake of graphene. And in fact, that's still currently used in most labs. But the reason graphene was interesting is because in order for the spectrum of electrons to come off of tritium to be precise, we have to make sure that the tritium isn't caught in a potential well that's too deep. And when we're talking about kinetic versus potential energy, it turns out that when you put tritium is like any other hydrogen isotope. It binds very strongly to things. And it binds typically at 4 to 5 eV of energy. So it sits typically in a well that's so deep that at the end point of the tritium, which only produces 3 eV of energy, it's not enough for the helium molecule that's produced to get out of it. So unfortunately, when this process occurs, you have to sum over all the possible excitations of a molecule in order to get the final spectrum of electrons, and that smears everything out. Now, in the development of a hydrogen economy, people wanted to find a way of storing hydrogen with a very light mass object, and so you can store it 6% by mass if you load it onto graphene. And so that's where a lot of the R&D went into developing R&D to develop fuel storage for hydrogen at room temperature. And that turns out to be ideal for our experiment because, in the same reason that you don't want the hydrogen to be too bound to your storage device so that you can get energy from it by interacting it with oxygen, you also don't want the binding energy to be too strong so that you don't smear out the energy of the final state. And so we managed to load this heavy nuclei onto the graphene. These were the first samples ever produced. We only achieved about 10% loading fraction. We want to go to 100%. So we developed yet a new method, which was a cold plasma loading technique, where you make a hydrogen gas and you cool it down and then you drift it onto the surface. And we have achieved the world record for loading hydrogen on graphene, 40%, but we think we can get 100% pretty soon. So that looked very promising. So the whole idea of using a substrate that can hold the tritium very lightly seems to be working out. Now, how about the measurement resolution? Well, it turns out that we had a lot going in favor of us for the measurement resolution because we want to measure a very small energy to a very high resolution. And if you imagine a good way of mimicking an electron, it would be to measure one infrared photon. An infrared photon has about 0.8 eV. And people want to develop high-resolution infrared photons where you don't just detect. So most people have a camera, they think the camera is detecting red, green, and blue. They don't. The detector counts photons, and what it does is it uses a little lens that statistically separates the different frequencies and counts the different components and tries to compute them. But today, especially when we look far into the space and we want to look at what's happening, we don't have the luxury of being able to statistically average lots of photons. So what we try to do is make devices that are so precise that we can tell what color each photon is. So we try to measure like a 5 eV photon to 0.05 EV, one photon. So we would know what process produced it. And so the advantage is that to stop a low energy photon like that, you only need a small, thin material. And everything goes better when the material is very thin. The amplitude of the pulse gets bigger when this number is small, and the response time becomes quicker. And so Our collaborators in Torino have now a world record resolution on infrared photon measurements. We can now achieve 0.05 eV, which was in fact better than expectation. We were hoping to get 0.15, and by redesigning this, we now believe that within a few months we'll have 0.01 EV resolution. So we've now made our mark. We've gotten something that we think we can use to separate the neutrino signal from the endpoint of the tritium. This is actually what the detector looks like. It's just a little pixel, and so as you can see, it looks like a bit of bricolage. But the way you start out with one pixel, and then you make wafer level arrays, and you multiplex them, and so the sort of focal plane that you would develop with this is actually not so dissimilar with the type of focal planes you would make for the Simons Observatory to measure microwave micron. And you can see that the pulse actually comes up and down. Well, it comes up in less than 150 nanoseconds, which is also a world record for speed for these devices. So that all became promising. This is a view of the device that we assembled in the basement of the physics department at Princeton to evaluate from the target to the calorimeter. This is a cryogenic refrigerator. That this process works, and that this device in between is that filter I mentioned early on. I'll talk more about that. Well, we've been sort of a victim of our own success because the numbers have looked so good. Many groups have asked to join in on this project and are all developing the different technologies in parallel. We have 7 different countries now. And again, this just started really at Princeton with Simons Foundation support. And now, in fact, some of our colleagues in NYU here in Abu Dhabi campus are work on the high voltage system. We have groups from Spain that collaborate with the Graphene company for the production of graphene, and the groups in Torino that do the microcalorimeter work, but we also have groups from Sweden and the Netherlands and Berkeley and Argonne, CITP, and also Brookhaven has contributed on. So it's moving into an underground location, and the reason for that is because now people are convinced that we have the measurement resolution we need, but now they say, well, how many events do you expect to see from the Relic neutrinos per year? Well, it's only about 10. And the scale that we're targeting for. So if you hold your hand out like this, it turns out that there's about 1 cosmic ray per second in this area. If you take that same, if you go with your experiment underground, the rate through that same area goes down by a factor of 1,000,000. So if you want to prove that you can make a detector, which intrinsically, I have to say, the experiment doesn't need such low backgrounds to be able to operate because it has several signatures that it sees. But intrinsically, you want to know what kind of backgrounds are in your system. And you can go down by an order of magnitude by installing a million orders of magnitude by going underground. And then the other problem is carbon-14. So, we're alive because we have the equivalent of about 30 feet of water above our heads in the form of nitrogen atmosphere. Now, the nitrogen-14, when it gets hit with cosmic rays, it likes to form carbon-14. That goes into our fertilizer, we eat it, and it ends up in us. So that's why you can carbon-14 date something, because you look at up until the last point in which it was digesting cosmogenically generated carbon-14 from the atmosphere, and then it dies and it doesn't generate anymore, and so you can date it. So you might ask the question, how much radiation do I have in my thumb? There's about 10 to the 24 carbon atoms in your thumb. There's about part per trillion of carbon-14 produced from the atmosphere. Carbon-14 lives a long time, about 5,700 years, but that's only about 10 to the minus 12. So you get about a count per second from your thumb. And if you use a new source of CO2 that has been developed for use in the Gran Sasso, which comes from the mantle, which is a bit over 5 miles underneath the ground, I think that usually comes from gold mines, but anyhow, they keep digging. This is a facility in southwestern Colorado that produces this source of CO2. It's 1 billion times less carbon-14. because you need to be underground for roughly 250,000 years. And so then you would only have one count per 100 years from your thumb. So maybe as a spin-off of this research, we'll make radio pure people, give them radio pure food to eat. And so what we do to produce graphene out of it is we actually convert CO2 to methanol. And as you can imagine, there's a lot of people doing research to convert CO2 into other things. And so we have a lot of setups to do that. And so we're developing this radio pure underground development. The other thing we're doing, is this filter. So we've used a traditional filter up to this point just to prove the technology. And I hate to do this, but I can describe this previous filter in the way you would compare a Galilean telescope to a Newtonian telescope. I don't know if you know the difference, but a Galilean telescope is a refractor telescope. And this is the biggest one that I could find that was made. It was about a 500-pound lens. It's in Wisconsin. And it bends parallel light in to a focal point, which bounces up to the objective, and you look at this ratio. And you need quite a lot of weight and precision on your lens to be able to get this to work. If you look at a modern optical setup, like used in the Atacama experiment, use a reflector technique. So a reflector was developed, so Galileo developed in the early 1600s the refractor method, and Newton developed the reflector method in the mid 1600s. And so that bounces light so that the equivalent focal length is spread out over many bounces. And so most optical things that collect light do the reflection method, including like your home astronomy telescope. That short thing will have a little mirror in the middle, and the light comes in, hits, bounces off that mirror, comes up, and goes in the objective. So we had to develop the electromagnetic equivalent of the reflector telescope. So you can see that they didn't overdo it when in the astronomy in terms of how big they made their reflector telescope. We have overdone it in particle physics. So you can see this is how sort of bigger than a little small German town. And so that device is called Katrin. And you can imagine that its focal plane is this big 10-meter diameter center part. And then there's one focus that's done from, and that works like a very good filter, but no one could ever imagine scaling such a thing up because this already is limited by the fact that the vacuum here has to become better and better because you have low energy electrons and they have to travel farther distances. So it's inherently limited. So we developed a new technique, which is a reflector method, and it allows us to stretch out the same focal length over many, many bounces. And so we've been able to use this method to design a system where we have our target mass, the graphene. The electrons are emitted, they're guided through this reflector method, and then we have this high-precision calorimetry at the end. And moreover, because the electron is going back in a nearly uniform field for part of this range, we can actually figure out, using a method of precision RF detection, roughly what energy the electron is, and so we can even filter based on that. So this is designed to be a 3-meter disk. And if you've ever, the final experiment doesn't have to go that far underground, but it'll go underground. And if you're transporting something that has any kind of radioisotope in it, you have to design it in such a way the isotope is going to be molecularly bound on the target, the vacuum volume is not so small, and so it's an engineering feat to make this project scalable to the full target mass. So we're focusing on making these individual disks that have all the precision we need, and then you need many, many of these disks. You need like 100 meters stack of these disks, but we're trying to work on the one. So that's where we are for the experiment, and I hope I've given you a flavor of what we've been able to achieve. But let me try to emphasize what we want to learn from the neutrinos. So this is a wonderful article that was in the Quantum magazine just last month. And it summarized some of the ideas related to this very earliest period of the universe. So the first point is that if we had sort of our naive view of what the Big Bang was, that we started with a singularity and we expanded out to this universe that we have today, it doesn't work. Gravity wants to make a much more clumpier universe than the one we see today. We would never have that celestial ball that was so uniform. Okay, so that doesn't seem to work. So the idea that was come up with, and is one of, I think, I would say the mainstream understanding of the early universe, is that maybe for whatever reason, there was a little flat space of space-time that existed already, and that it was mainly filled with dark energy, cosmological constant, and it expanded exponentially. And it gave us this initial conditions in which suddenly, for whatever reason, matter and radiation started to be created, and then everything would evolve according to the way that we see today. A lot of us are not comfortable with this, in that not only it's not clear that it really makes physical sense, in the sense that when you go through this inflationary period, it turns out quantum mechanics tells you that, in fact, maybe you're creating not just one universe, but many universes during that expansion period. And what is the evidence that this is actually the conditions that led to this magical initial state? So there are many, not many, I would say they're very hard to come up with theories that work. There are new ideas. A couple of them are described in this article about how the universe came into thermal contact in a collapsing phase, so that in some sense the Big Bang is the feedback to gravitational collapse, in the same way supernova explosion is the feedback mechanism that counters the collapsing system, some kind of blowback. It's not clear whether that's true, but it might be the case that the fluctuations, the small fluctuations that you would see from something that avoids the singularity, whether it's because of some other substance in the universe or some kind of angular momentum in an expanded space-time, maybe it has some signature. So what could we possibly do with the neutrinos to look for such a signature? So if we go back to this original celestial ball and the paradox of causally disconnected regions of space, the current understanding from inflation is that there was some point in the far past. In fact, our current understanding is there was no t equals 0. The universe evolved out of a space which is inherently symmetric between space and time, a space that's so-called a de Sitter space. I've tried to draw it here. I'm not very good at this, but you imagine an hourglass, and the flat dimension, you would slice it like this. So if you imagine all of these lines, these are like these lines here. They all come to some common point in the far past, and these are steps in time. And so for some reason, we came from a universe that could have existed forever, and it pulled out of this universe when the expansion rate was so rapid, because it's growing exponentially, that the causal region, the sort of co-moving Hubble radius, got so small, smaller than the distances we can probe at the LHC, that something happened. Some kind of length scale was reached in which a speed bump was hit, and all of the kinetic energy from the expansion got dumped into matter and radiation. We'd love to know what that was. So in the current methods that we use, when the universe was rapidly inflating, fluctuations, so everything's expanding very fast, and fluctuations that are created get stretched. They get stretched to some very large size, but they leave our causal connection because of the Hubble law. And it kept going and going and going until something happened that dumped a lot of matter and radiation. And then the universe started to expand at a slower rate because of the potential well of the matter and radiation. But initially, it was filled with radiation, and radiation smoothed everything out. But once the radiation dropped below a certain level, which was 75,000 years after the Big Bang, matter started to dominate. But then a wonderful thing happened, which is that fluctuations which had left our horizon in the inflationary period, when they came back at this period, they produced acoustical waves in that plasma. And so that is actually where we get most of the information about the early universe. Now, ironically, the largest angular scales on the sky actually come from the earliest period of inflation, because those are the ones that got stretched out the most. And we can see them. We can even see that the amplitude is slowly going down, which is something called the spectral slope, which is predicted. But unfortunately, we can't see earlier, or in other words, we can't see at this later period of inflation in which we switch from being from a de Sitter space to the kind of space we live in today. So with the neutrinos decouple at this much earlier period. So the chance that there are density fluctuations produced here, which somehow relate to some theory that tell us why the universe chose to switch to matter and radiation, they could have imprinted themselves on the neutrino density fluctuations, which then decoupled and weren't smoothed out by everything else. And there could have been other physics at the end of inflation, which was not the physics that was the thermal production of neutrinos, because we're probing very high scales there. And so maybe there were some right-handed neutrinos that were produced there, and they're still here today. So, you know, people like the neutrinos because we can look closer to the end of inflation. Now, neutrinos, when we count them, it's hard to point. So when you have optics, you can point. You can say that patch of sky, this patch of sky, and you can do correlations in angle. When you count the neutrino, you just get some count rate. But we came up in these last 2 years with a method of pointing to the sky, and it turns out because the tritium nucleus has a spin and the rate of capture depends on the orientation of the neutrino with respect to the spin, we can now actually point to the sky by pointing the spin of the tritium nuclei. So with that technique, we have this dream, at least, a path forward, in which we think we can make yet another celestial ball, in fact, 3 of them, because there are 3 masses of neutrinos, and we believe we'll be able to probe 3 different levels of evolution of the neutrinos under gravitation. So the most massive ones will sort of cluster hemispherically, but the lighter ones may encode the information about the model which describes the physics that led to the inflationary universe. Okay, that's all. Thank you very much.